The next talk will be given by my illustrious co-chair, Wajiha Iqbal, with Hiesinger, Vanderbogert, and Head as co-authors on a source of young ages at Apollo 15 landing site. I can actually time for you, Wajiha, so please take it away. And I think you're muted if you're.
Sorry, too many buttons. Yes. So now you can hear me?
Yes, I can hear you fine.
Okay, so probably you can see me now too. So in this presentation, I would like to propose a source of the young ages, which were noticed in the samples collected from Apollo 15 landing site. And this study is a small part of a bigger project in which we are testing and we are possibly improving lunar cratering chronology function. So as I noticed today, we have people from various geology field here. So I would like to describe a little bit what lunar chronology function is here. So on y-axis, you see a logarithm scale, which is represented by the value n1. And this value you gain by measuring crater size frequency distribution. So in general, I can say this number is representing crater density of certain geological unit for certain range of diameter. In this case, here is a 1 kilometer. And on x-axis, you see time, and you see time in billion year, and this time is normally considered from or taken from isotopic ages of the samples. So how do you calibrate this calculated lunar chronology function? For this purpose, we prepare detailed geological maps of all landing sites. And then we identify a homogeneous area, geologically homogeneous areas on this geological map and measure CSFTs. And from there, we get N1 values that we represented on y-axis. And then we also investigate composition and isotopic composition of these samples and isotopic ages that were determined through these samples. And that's what we represented on x-axis. And by correlating these two values, we could get a calibration point that that can confirm as validity of this chronology function. So as I say, for preparing geological maps, we use wide range of data. We use a lot of data that is like image data, for example, LRO, WAC, and NAC images. We use different DTMs, and we use various spectral data. And we use this data on different resolution. And with this information, we can prepare very detailed geological map, and we prepare the geological map for all landing sites. And here I'm presenting a geological map for Apollo 15 landing site. So this is overview around the Apollo 15 landing site, and this green triangle in middle represent position of the lunar module and in the east of Rima Headland. We use spectral data to map various Mare units here. And here, what is different from previous maps of this area is that we mapped Aristobulus and Autolycus craters at the red Sustinian, on contrary to what previous authors map or people map these craters as Copernicus. And this is decided on base of CSST, relative positioning. And also we noticed that this ejecta material from Aristobulus is different due to the compositional differences. We also prepare a geological map that is a more detailed geological map around the lunar module. Here again, green triangle is representing position of lunar module. These dotted lines are representing traverse that were taken by astronauts to collect samples. And what we notice here is most of the traverse and lunar module is present on a ray material that is coming from northwest direction. However, there are also kind of young craters around this traverse, like Bridge crater or St. George crater, that could also have material present on these traverses. So so in most of the samples that was collected, most of the regolith and impact breccia samples that were collected on these traverse contain class of creep-rich basalts. And there are also some samples that were collected near Spur crater, which also which are actually samples of creep-rich basalts. But some of these samples show age of 2 billion year, which was interpreted to be that they were heated in a common event around this time. And this age of 2.1 billion year is mostly correlated by Bogart and Ryder, for example, with Autolycus crater. Yeah.
4 minutes.
So but here I'm showing you a thorium map in comparative to our derived geological map. And what we know here is that area around the landing site is deficient in thorium. And being deficient in thorium means that they are lacking creep-rich material, which means that the Mare basalts that are around this lunar module are not creep-rich. So there are 2 points. So there are 2 points in blue which are showing higher thorium anomalies. That is one near in the south of Archimedes crater. And this area is normally in older maps are mapped as opinion bench formation here. However, in our map, we noticed that it's a mixture of many different formations. It's a mixture of ejecta material, light plains, and various mare. However, the pure thorium anomaly we noticed around Aristoteles crater, and this the extent of this this anomaly is very consistent with our mapping units as well. So it means that if there is a creep-rich material coming on this near landing site, it is possible coming from Aristoteles crater. So considering that in mind, we try to get some N1 values for Aristoteles crater, thinking that it might be also around 2.1 billion years. But getting ages on younger crater is very tricky. You have to deal with a lot of secondary craters. There are too many slopes. So it is very difficult to find these N1 values on young crater. We use several data. We use back data. We use Kaguya data. However, on NAC data, we could determine 2 reasonable areas on crater terraces, and we got consistent N1 values for this area, which also indicate it could be of 2.1 billion year old. However, because these areas are too small, we are concerned about also errors on these areas. And anyway, if we take these values, N1 values, what we gained on these areas and correlate them with the sample ages of 2.1 billion year, we are able to get a calibration point for lunar chronology function. And this gain calibration point is again very consistent with measured lunar crating chronology function that was measured, that was derived by Neukom in 1983. And that's it for my talk. Thank you.
All right, thank you, Wajiha. Are there any questions in the chat? I'm not seeing any right now. There is one here, again from Ichi, who's asking, I may have missed something. Are the materials from the 2.1 billion year old crater sampled? If not, how does it help calibrate lunar chronology function? Oh, and I think you're muted.
Okay.
Yeah,
Sorry. Yeah. Yeah. So 2.1 billion year age has been found in samples. So it was found in impact fracture material that was in creep basalt samples. And this was it was considered that it was reheated. This basaltic material was reheated at 2.1 billion year. And the idea was where this cage can come from because it is transported there. And we were looking for a source where it is transported from.